Now tell me, is this your plight? Do you sit there and write queries? You struggle to get, you're trying to get the query correct, implement it properly, get it to return the right result set, and then you take it into production and it seems to fall down on its face. It can't be performant. And then you run into, maybe you've tried it, you've taken it to different systems, or you figure out how to get it working, and then you come to a place like Cockroach to be a distributed environment, and suddenly it feels like you're fighting the same battle again. Well, we're going to talk about what's at play. What's when you get into some of these queries where you have one-to-one relationships, one-to-many relationships. What we're going to talk about cardinality and all these kind of things. But before we get to that, I want to bring in my good friend Felipe here, who we were doing a bit of chatting before the show got going. And how you doing today?
Hey Greg, how you doing, guys? Again, happy to be here just to learn from the master and learn more about cardinality. So yeah, happy to be
Cardinality.
here.
That's Yeah, great. Cardinality is one of these funky words. You go look it up, and there's actually like three or four definitions. And to kind of set the stage, the you have things like cardinal numerals. A cardinal numeral is just one, two, three. There's the counterpart is an ordinal number. Ordinal numeral is first, second, third. So we're talking about one, two, three, like counting. But then when you get to cardinality, it means it's sort of a branch of mathematics, which is like how many elements are there in this set? Is there a finite number of elements in this set? And you start to get into relationships of, well, this set has this many items and that set has that many. Is there some relationship between the two? And what I decided to do was to go and go get my iPad here so we could look at some of this. So, if we're talking about cardinality, oftentimes this is a situation where we've got some kind of table, full of rows, and there may be a relationship. So let's imagine we have an order table and each row is an order, and it's got all your columns in here. So you have things like, you have an order ID, um, for given order. There's other things. Maybe there's a transaction ID, a payment ID, things like this that link into other systems. Well, we can focus on one of these. We can talk about this payment ID for a given order. There's probably going to be a payment, but you typically don't necessarily have all the details for the payment here. Let's zoom in a little so you can see it better. For example, there might be some kind of other table, your payments table. And this thing can have things like price, taxes. It may have a transaction ID associated with the payment. These are all your different columns. And don't forget, we're going to have some kind of payment ID related to this. And it's this relationship here that lets us draw this line and say this is a one-to-one relationship. Every order has one payment. Every payment is associated with one order. And you can also go on to say, um, if I let me clear this out here and let's be super clear. It's a 0-to-1 relationship because the order can start before any payment is made. You put together the details of the order and then you go and collect payment from the client who's making the purchase. So it it shifts from zero payments to one, but it's never more than one. There's never more than one payment for a given order, or at least that's the way you design your system. Okay. And we call this thing is a form of cardinality in relational databases. So big fancy word, branch of mathematics. You can go read really dry, dusty stuff that maybe is a little hard to grok, but it's a pretty simple concept. It's what's the relationship between this table and that table. Now let's clear this out and let's pick a different situation here. Whew. So I'm using Procreate to do this. This is my little thing I use to draw in my spare time when I'm having fun. But I thought, hey, this is a great thing to use here. Let's pick another scenario. So let's go back and we've got our nice order table. But what's an order made up of? Well, an order is basically, you can think of it as an invoice that a customer has to go make a payment for. So we just talked about payments, but an order is built up out of products that you put on there. So you can essentially say we're going to have another table here, and maybe we'll call it the line items table. So you can have, we have again an order ID to identify an order. Well, we can have a line item ID over here. So every entry in this table is going to have a entry line is going to have a line item ID in this table. But there's a relationship here. So a given order, we're going to say, can have one or more line items. So any one order, we'll say, can have many line items. And this is what we call one to many. And so this is a different kind of cardinality because we can no longer take the relationship of for every one order ID over here, there's one line item over here because that doesn't even make sense. We're going to have different stuff here. We may have, what are you selling? Well, you may have shoes and frozen yogurt in your order. So these are two different line items. Maybe the shoes are $19.99 and the yogurt is $2.49. And this is order number 157. So there's a relationship here that we have now a one to many situation. Okay. Kudos if you spot my reference here. I'm making a joke to one of my favorite TV shows where somebody's like, "You sell shoes and frozen yogurt? That's kind of weird." Um, so let's go look at what this looks like now. We've modeled the table concept, but let's talk about, okay, assuming that that's the structure you have, how do you go find something? Okay. So basically, we use SQL. So SQL is a nice thing we use. It's very easy to grok. It's been with us since the 70s. And the testimony to its success is the fact that not only do software engineers speak this, so do business analysts, program managers. Sometimes, we've seen other people have dabbled into it, and it's not complicated. A friend of mine told me years ago he was the lead for the software or the database development team, and he said it's not rocket science. So we can sit there and write a query. Let's go select star from order. Hey, nice select star there, right? Okay. From order, join line items on, we're going to say the order PK equals line items. And here we're going to assume we have an order FK. So in this situation, I could zoom it up here a little bit. This is our criteria for linking the tables together, okay? The idea is that there's a primary key in the order table. There's one for given order, there's one primary key for it. However, every single entry in the line items table that's linked to the order is going to have a copy of that primary key from the order table stored in its own column. This is called a foreign key, okay? That's why it's not order. We don't use PK because that gives the context as if it's a primary key here. No, it's a foreign key. It's a key found somewhere else. And this is what lets us define this relationship. Oop, don't mean to hit that. So if we go run this query, I think we said order 157, we can expect to get back a result set. We can get back an order primary key. I think we said order 157, but we can expect to get back, some kind of, let's see. Here, let me, I'm not going to put the tables, let's just put the columns, okay? And let's be choosy in what we put here. So we're going to have, let's call it item name shoes, and let's put price, item price. Let's see, $19.99. And then we're going to have another row, and we're going to have that same order PK, 157, only this time we're going to have frozen yogurt. And I think I said 249 or pretty close to it. And this is our outcome. So you can look at this and say, all right, this is a one to many relationship. We have one order 157, and we have two line items. And what you get when you In a sense, you're multiplying them together to get this complete result set. This is our result set. Or sometimes if you use this and then go on and do other joins against this, you can call this the intermediate result set. But this result set has two line items because in a sense, you could take one row from order times two rows from the line items table. One times two is two. Therefore, you should expect to get two. And this is what you call a Cartesian product. The Cartesian product is when you match every value from this table against every possible combinations of value from that table. All right. So it's a Cartesian product, and then it flanges down and filters out anything that doesn't match on this thing. So this is how we get a result set. That's not too, in my humble opinion, that's not too hard to grok. That makes straightforward sense. Got to make this thing eraser big to clear this out fast. So the thing that I opened up with talking about is there's kind of a struggle when we go write a query. You go write some query and it's like, how do I make this? First of all, I need the answer to be correct and I need it to be performant. And how do I do both of those? And my general suggestion is you need to start and write the query correctly first. So let's get the right results back. And then from there, you need to look for different ways to optimize it to figure out if you're doing if there's something that's missing from your data structure. Okay. So let's go and pick another example. I want to share an example. And this is something that I dealt with one time. So I one time worked on a system and we had to monitor equipment in the field. And so out in the field, out in the great big wide world. Well, if we're going to say the great big wide world, we can maybe pick a structure that's more here. We'll call this the continental United States. This is my kindergarten grade artwork. Okay. So what you can imagine is if you're monitoring devices, there's a device here, there's a device here, there's a device here, there's a device here. If you zoom in, there's a little light, radiating its status. This one's got one too. Bloop. This has got its own status, a lit up light. Are you enjoying the artwork? So all these devices are reporting their status, okay? And the whole idea is this traffic is flowing back to your operations center and you're going to correlate on it. And then what you're wanting to detect is, alert, alert, alert. Suddenly this one, that is not what I picked there. This one goes red. Now, if you're listening to this on the replay on the podcast, which you can either be watching us live on the live stream, or we need a banner where you can find out. If you can go find it on Spotify. If you go look for Let's Select Star Show, you can be tuning in and listening to this on your commute. I've kind of drawn a big map, okay, and I've drawn 4 different devices spread around on the map, and they're all reporting their status. But one of them goes bad and it throws an alarm. It registers an alarm that gets transmitted back to the headquarters and it goes red. Okay. So the whole idea is somewhere somebody needs to detect that. And so the message you get is, oh, let's go back to black. Let's make it a little bigger again. You get this alarm that server 158, is down. This is this piece of data that you're handed. So what do? You need to go look in a table filled with machine names. And you need to correlate that. So you're looking for server 158. Okay. So you're doing a lookup. Right now, the database says that the track state of the device says it's up. Well, essentially, you need to update it and say that it's down. So what do we want to do? We want to write an update. Update devices Wait a minute. Let's do this correctly. Okay. Set state equal to down where host name equals server 158. Okay, so this is a real world problem. Your monitoring device, it goes down, and we've pulled it back to map to a select statement. Well, not a select and update statement, a SQL statement that you're needing to update the system. You want to update it so you can then all your error handling stuff trickles down from that. It updates on somebody's display. It alerts somebody to call the teams to go out and fix the device. And so you need to be able to do this kind of update. And what happens when you have this kind of where clause? What database engines do is they're like, well, I need basically the database engine needs to find that row in that table and update that one column. Okay. So fundamentally, what it needs to do is it's going to scan the whole table. Okay, because that's what it knows. It's going to scan the table until it finds that host name. And so the question arises, what's the structure of the table? Can this table have more than one row with the same host name, or is the host name a unique value? If it's a unique value, the database engine knows that when it finds that row, it can stop. So maybe that happens to be the second row in the table. Good, it can stop there. But what if it's the next to last row in the table? Then it has to go all the way through every row almost to get there. And if you go into a distributed system where the rows have been chopped up and spread out in ranges across the enterprise, and you have database nodes running on the West Coast, the East Coast, Western Europe, Eastern Europe, it's going to have to go to every range, and you're going to have to start eating the latency cost. So one of the first things that we do in this kind of scenario to make this feasible, has anybody got it? Can you guess what I'm about to tell you to do? Put it in the comments. You know what I'm going to say. Everybody's favorite thing is create an index. That's what you want to do. You need to create an index because an index is a shortcut to getting to specific rows of data. Okay. And fundamentally, it's not, again, this is not rocket science. It's basically create index on, in this case, what are we talking about? Devices dot host name. Now, there's a chance that the statement that I just wrote is a little off, that the syntax is not 100% correct. I think it's correct, but fundamentally, that's what you do. This is what the SQL looks like. Create an index. And you're telling it what to make it on. You're saying, I need to index this host name. Because what it does is, we already talked about, we've got this nice little table here. And it has, server 158. It's got server 1527. It's filled with stuff. There's a million devices. Who knows how many devices? And there's server, 001 way at the bottom or something. They're randomly distributed. There's a primary key, but this is not the thing. This is the host name column. And what Cockroach DB does, every database, the way they implement every database engine, relational database engine has indexes. But the way Cockroach DB implements it is essentially it makes a new table. And what it's got the value that you made it on, the host name, okay? And over here, it then has the primary key for that row. And what it does is there is the value here. I'm going to draw a strong line here. Okay, I'm still working here. The value on the left is the key, okay? The key here, and it's sorted. So what happens is there's an entry for server 001, and it's got the key that then points to this row. A little further down, we have server 157 and its primary key. And let's assume 1527 is the last server in the list. And at the bottom of this is server 1527 with its key. So the whole thing you can do, well, the optimizer is doing this for you. You run the query, update device, set status equal to down, where host name equals server 157. It's able to automatically grab this index. It says, hey, there's an index based on host name. You're doing an update based on host name. I can use this index. And it's able to take the index and chop it in half. It can sit there and say, I'm going to go to the midpoint because it knows that it's sorted. It says, is the value I'm looking for above or below this? It's above it, throw that away. Take what's left, split it in half. Is it above it or below it? Above it. So throw this out. And then it's able to get to that in record time. And this has got the link back to the actual row. So it can take it to where the key, it's basically got the primary key. I should have drawn it. It comes in here to the primary key. This is the primary key. Is that messy as all get out? So if we're going to go and do this, update device, set status equal to down, where host name is equal to, whatever your host name parameter is that you feed it. This little clause is your clue about making an index. It's like, hey, maybe that's a good candidate for an index because that way it's able to filter rapidly to get to the row that needs to be updated. Now, earlier we were talking about one-to-minis, okay? So, we talked about here was we just talked about going after a single row in a single table. There's also situations, before I go to the minis, let me add one other thing. If you're updating a single row, one row being updated, and that's all you're trying to do, then what I just presented is a very nice, simple, elegant, great way the index is going to serve you well. But let's think of another situation. What if it's not one row? What if it's 10 rows? What if it was 10 rows that you need to update? Well, the index is probably still going to work because it's going to go back to the index and find the 10 entries. It has to do a little more legwork, but that's still faster than scanning the entire table, especially in distributed fashion. If you got the 10 rows, okay, that works. But what happens when you run into the situation where what if you're having to update 10% of all rows? What happens there? Now what you start running into the phenomena of I need to go look in the index to get the primary key to then go back to the table. So there's a little bit of an overhead to go to one to then get to the other. And maybe at 10% of all rows, it's still more effective to go to the index. But can you see where I'm going with this? What if it becomes 25% of all rows is what you're needing to update? Well, it's again, if you're updating 25% of all rows, there's a flat out cost of that that's unavoidable. The question is the index serving you or not? But you can finally run into a situation where it's like, what if the update I'm doing is going to hit 90% of the rows? In that case, if it always goes to the index first and then it's going to come to the table, you're at a point now that you're updating so many rows that in a sense, what if this was a million rows? And what you need to update is 900,000 of them. So there's a flat out cost to going to 900,000 rows. But what if you had to go hit the index 900,000 times? There's a cost to going to the index. So the first is the table, the rows, and you may end up the situation where it's actually, you're doing, you're accessing 1.8 million bits of data in that context. So, this may be a situation where it's better to do not use the index, and just update the whole table. Just scan every row and hit the table, because in this context, you're hitting all the rows anyway. And so the idea is to look for those scenarios and try to make them as few as possible, at least try to avoid the situations where I'm having to update every row of the table. Now there's a message in all this to temper, we can talk about cardinality, back on the topic of cardinality is, it's basically counting. And so we talked about what's the situation if you have a million rows, okay? That affects what you do, whether you're using indexes or whatever, how you're going to use indexes. But what if you have a table that has 10 rows, okay? Is a full table scan a problem for 10 rows? Probably not. They probably all fit in a single range. Interestingly enough, we're talking about Cockroach DB, the database you just can't kill. I've worked with data sets where the million rows all fit into a single range because the total size of the data itself is small enough that it actually fits in a range. But I'm trying to get the concept across that you can either be working with a huge data set that's going to be spread across lots of ranges, distributed across lots of nodes, and there's a whole lot of latency, versus a very tiny data set that if you're going to update every row, it doesn't matter if it do a full table scan. Okay. If it's 10 rows, then it's no big deal. What's an example of this? Well, what if you had a table called device status? You're in your data analysis, you decide to put all those enumerated status types into a very tiny table. You could have, if you could have, your device status table. You can have up, down, degraded, in maintenance, you know, being provisioned, okay. Okay, I came up with 5 without even thinking about it. I'm sure we can brainstorm another 5, but the idea is you've decided in your data design and your entity relationship mapping that you're going to put this enumerated value in a table, and that's fine because that makes it where the relationship is such that, okay, if I'm going to add a new state to it, I just need to put it here. Or if I'm going to update one of these values, I can just do it here. Okay, I do it in one place. There's one copy of this given value in one place anywhere. And I know that when I update it here, it's going to be picked up everywhere. The side effect of this, just to put all the cards on the table, is that when I select, if I'm going to select from the devices table, if I'm going to look up, I want to look up server 157 that we're dealing with, where host name equals server 157. I left a gap here on for a reason. I can't, that's not the full story. I can't get all this information now purely out of the devices table. The devices table had the host name, but it doesn't have the status now because I've moved that to a different table. I'm going to have to join a little bigger eraser here. Okay. Okay. So I'm going to have to join with the device status table on devices.status. We'll call it FK equals status PK. All right. That way it's going to join. And this is, what do you think this is? Is this a one-to-many or a one-to-one relationship? Well, this technically, the way this would be a many-to-one relationship, because many devices can have one status, can have the same status, but each device has one and only one status. Okay. So this is what we call a many-to-one relationship. And this is the situation where nobody's going to really look up. Well, maybe they will. I want to look up all the devices, or for a given status of up, I want to see what all devices are in that. Usually they don't do that. Usually they say fetch all the devices, give me their statuses, now sort by status, that kind of thing. So I would still do the query like this. So let's go to a one to many relationship. So let's clear this out a little here. if you want to know, in the intro, it says I wrote 200 queries, over 200 queries, and it was on this system. And so it got burned into me how to write these statements. So I want to break it to you. We like to think that a device is up or down and that's all there is to it. No. Typically, this nice big server with a nice little light, nice little green status light here, is usually built out of other devices. So instead, this device has two cards, okay, some kind of little card, and the card has its own little status box. And this device has 4 ports on it. Okay. Yeah, most of the time, each of the cards is green. Each of the ports is green. So if you're listening in, imagine a big old giant box with its own status, maybe it responds to ping checks, it's up or down, but it also has 2 cards. Each of the cards, see, you can swap out. This is a device you can pop out the card and buy the upgrade to do it. And then it has its own ports. Actually, let me finish drawing it. Each of the cards also has ports because there's not much of a card if it doesn't have a port. So each of the 2 cards I'm drawing 8 ports. So let's pencil in the status of this thing. Okay, so each of the cards, you've got nice, everything's green, and then this happens. One of the ports goes red. So in all this thing, let's count it up here. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27 different things reporting on their status. Okay. And it's fun in the game of SNMP, network management stuff. Even each device may have multiple error codes it throws, and you have to decide which ones actually count. So in this thing, we have, what did I say, 29 devices or 29 things reporting the status, and one of them goes red. And you need to correlate it. You need to go divine what's the deal. What has happened? So now we need to model this. This one's gotten kind of complex. So we need a device table, but then we need a card table. And finally, I'm going to draw it way down here in the bottom left corner is we need something called a port table, okay? Well, one device can have 0 or more cards in it. There's some devices that don't have any cards, and there's some devices that do have cards, okay? So you need to capture that. You can call it a one to many, but actually it's a 0 to many, which is, for all intents and purposes, the same cardinality. Now you can have a card, one card. We said we never had cards that didn't have ports. So it's a one to many relationship here. But the way we draw it, the device itself could have 0 to many ports on it. So this is a complicated diagram to get into verbal mode, but one device can have 0 or more cards, and then the device and the cards themselves could each have a certain number of ports on them. And the whole thing is you're trying to all that you have. Let's imagine all that you have is a host name coming in from the field. The host name is in the device table, okay? And then you've got some identifier, and that identifier is either in the card table or the port table. And now you have to go figure out where it all is so you know what to update. So I am going to simplify this because this thing was a bit of a nightmare. Let's just take this little relationship out of here. So what I'm doing is I'm just saying every device has one or more cards, and every card has one or more ports. Device to card to port. And we can further simplify this and say let's just stick with cards. Let's just forget about ports altogether. Okay, let's keep it simple for today's live stream about the database that you just can't kill. All right. So I'm going to clear this out, and I need to run a query. So I got in. So the alerts I got in look like this. Either the alert is against server 157 and there is no identifier. If I just see that, I know it's in the devices table and that's all I need to do. So I'm going to update devices. Now in this case, let's forget about that separate table that had the statuses. Let's just keep it all in the devices table. Update devices, set status equal to down where host name equals server 157. Okay. So this is the query that I need here. Update devices set status equal to down where host name equals server 157. And this is where that index comes in handy because the index is able to sort the index is sorted. It's able to quickly find the host name. It then gives it the PK. And essentially, the point of index is it tells you where the row lives in the database. In Cockroach DB, that translates to it tells you which range it's in. So it can say it's in that range, and here's the PK for it. So Cockroach DB is then able to jump to that exact range and get it. Okay. Now, I'm not going to talk about covered indexes, but there's a way to make it even faster. In fact, there's the second video that's on this playlist. If you go to the YouTube channel, talks about some of that stuff with our prior director that used to be here. We did a great show talking about how to make stuff more performant with covered indexes. But let's do the thing where the alert we got was against server 157, but it was card 02 and it's down. Card 2 is down, whatever that means. Okay. In that case, the status of this is not on the device. The status of this is on the card. So before I write the update, why don't we write the select first just to kind of grok it here. So we're going to do select star. Now, put in the comments if you think select star is something to use in your production queries. Or if you're not supposed to use it, can you tell me why? Put that in the comments, and we'll look for it after the show. Which is funny because that's the name of the show. That's why I named it that. So I'm going to select star from devices, and then I'm going to do this. I'm going to join cards on, and I'm going to use shorthand here. Device PK equals device FK. So this is going to give me back a list, and it's going to give me back a list of every device that has a card. And it's going to join it on the assumption that the device PK in the device table matches the device FK or foreign key in the card table. Let's call this. Yeah, okay, we're using consistent syntax. Okay. Let's flip this and let's try. It doesn't look as good. Let me do this. Okay. So now there's a problem right here with this query. Okay. There's a problem right. We already talked about, we just had an alarm come in that was at the device level. Okay. The device reported an error. Are we able to find an individual device here? No, because it's doing an inner join. It's joining only giving us rows where there's a device and a card. Okay. What we need in this context is we need what's called a left outer join. Okay. Because it means the card is optional. Okay. The It's a little confusing if you think left, top, right, bottom. Essentially, the left side of the query is if you're walking down the query, the first thing you see is the left side of the query, the devices. The nomenclature kind of rises up out of the fact that typically you list on the left-hand side of the join clause. This is the criteria from here. This is why they call it left, but in a sense, it's the first table is this is the left part, okay, and this is the right part, okay. You can actually write the on clause. You can flip it and have written it backwards, but this is still what's left and right in this. An outer join simply means I'm the right hand part is optional in a sense. If there's nothing there, if there's no match, it doesn't matter. It's still going to list the item on the left. The item on the right doesn't have to be there. So I'm going to do select devices left outer join cards on device PK equals device FK. Oh, I keep hitting the wrong button here. Now, just as a reminder, let's look at this table structure. So we have the devices table, and over here we have the cards table. So we have server 157, and we have card 1, and we have card 2, which I just drew as card 1 a second time. Let's amend that. Card 2. All right. This has server 157 has a primary key. So this is the devices PK. Let's call this one, we'll just call it 001. You should be using UUIDs, but I'm going to get writer's cramp if I try to write a UUID by hand. So we'll just call it 01. Over here, there's an order F, not an order, device FK. In this case, 001, 001. So here we can see this one-to-many relationship. Right here, I've depicted card 1 and card 2, and they both have 001 primary foreign key to point back to the server row. Okay. So these point to this one. So when you join them, you get back 2 rows. If you do the left outer join, you're going to get back 3 rows because first it's going to join the server 157 row with nothing. Okay. You're going to get back server 157, and then you're going to get null for the columns from the card table. Okay. In fact, why don't we, instead of saying that, why don't we just show it? Okay, let's clear this out. All right, you got everybody having fun? Sit there and hit the like button if you are. Okay, so when we run that query with the left outer join, we can expect to get a host name. We're going to get the primary key. We can also get the card name. Oh, don't want to leave there's some critical stuff I'm leaving out of here. There's a status. Remember, there's status at the device level. Then we have the card name. Then we have another here. Let's I need more room, Captain. Okay. There's a status at the card level, and then there's that foreign key. Okay, let's draw that. Card name. All right. So we got server. Okay, we got 01. This is our select query that's going to do a left outer join. Left outer join. Okay. So we've got server 157. And the first one it's going to do, it's going to join it, and it's not going to go to the card table. Okay. That's just the nature of the beast. Okay. It's going to join against a null card entry. Okay. So the server itself is going to have its up status, but this is going to be null, null, and null. Okay. Now, the next time, the next row it's going to do, it's going to fetch the same piece of data, but then it's going to match. So it's going to find card 01 and card 01 status, which is up. And the foreign key in card 01 is the same. It's going to point back to record 1. And then it's going to, one more connection, it's going to find card 2. And then after this, we can have, server 1528, whatever. So in this situation here, we've got 3 rows coming back, one for no card, one for card 1, one for card 2. And so this is the point of view when you write this query your application code has to deal with. Okay. This is the result set coming back. And so you have to map it into your POJOs or your objects, whether you're using Java or TypeScript, whatever. You need to map it on there, and you need to decide how are you putting this on the UI for your operations person to look at. You may have to do a little business logic that sits there and says, I'm going to look for that row that doesn't have a card, and I'm going to put it at the top. And then for the one that's showing the server 157, I'm going to find the rest of the rows for the same host name, and I'm going to put the cards in a sub list. Okay, that kind of thing. You have to map the code to that. This is the stuff you have to do. The database is handing it back to you, saying, this is what you asked for. This is exactly what you asked for. And in this structure, you'll notice the PK and the FK match, except for the first row. And it's okay if they don't match, but it's never going to be the case that the PK and the FK are two different values. So you're not going to have PK 001 and FK 058. That's not going to happen. So with this structure in place, now we can start to figure out what update do I need to do if I'm going to update a status. So let's clear this out. I need a little bit bigger eraser. Okay. Come on. Okay. So I need to look from an application perspective. I need to look what's the alarm? What alarm came in? Server 157 down. If I could spell the word down. Okay, I don't need that. Server 157 is down. Now in this situation, no card identifier. So we know it's a server only update. So I can do that first update we did a couple times. Update device, set status equal to down, where host name equals server 157. No problem. Okay. But maybe the next alarm looks like this. Server 157 card 2 down. Okay. Well, I need to update the card table status, not the device status. So we may start doing this based on everything we've done. We've done some joins, left outer joins. Let's see if I can do this. Update card dot status equal to down. Well, wait a second. What do I put here? That's a I would have done a join. I would have been joining something. Is there, let's see, you select from table, I'm trying to do an update. Here's the thing. When you do a join and you join two tables together in a relationship, you can't update that because that's an intermediate result set from an updates perspective. So what I need to do is I need to update cards, set status equal to down. But I need to write this where clause. I have to find this. So I need to find which card. There could be a whole bunch of card 02s in the system, but I need to find the one linked to server 157. So this is where I need to do, maybe I can do this. Let's do this. Let me shrink the pencil down a little. Okay. Select card PK from card join devices. Cards join devices on oh, let's see, on device PK equals device FK. Okay, so what I'm doing is a subselect here. So I'm trying to find a card PK that I need to use. I'm trying to find it from the cards table, but I got to join into the devices table to link it. So I make sure, well, here. Okay, this is doing the join. I'm running out of space. I need a where clause, where host name equals server 157. And then I need a closing, I need a closing one for the top where card PK is in this. So I can do this. So what I need to do, update card set status equal to down where card PK is in. I'm going to write a subselect that's going to come back to me with the card PK. Now, the way I've written that, it's still not correct. I'm going to, can you spot where the problem was? Let's try to rewrite it and I'll try to be more space efficient. Okay. Okay. Update. Okay, let's pause for a second here. This is why writing SQL, it takes a little bit of time. It's not complicated, but sometimes it's a little tedious. Okay. I was writing the select or the update and I got pretty far and I realized I got the host name correct, but not the card name wasn't in there. So it takes a little bit of work to get it, but once you get the hang of it, it's really not that hard. Okay, so let's do this one. Update card, set status equal to down where card PK is in, and I'm going to have a big old, I'm going to leave myself some room here to do this. So I'm trying to update the card table. So here I'm doing this correctly in the sense that I'm updating one table. And the idea is to update one row of that table. So I'm going to pick I'm going to do the PK in this context. So now I need to find the correct primary key. So I'm going to zoom in and write a subselect. Select card PK from, and I want to map this. I'm going to map this. We earlier did the device. We did device to card relationship. So I'm going to do this device from device join card. Oop, there. Join card. Oop. Okay, go back to pencil mode. On device PK equals device FK, where card name equals card02 and host name equals server 157. Let's zoom out and look at this thing. Okay. So here, okay, update card, set status equal to down where card PK is in. So I'm gonna I want to match on that. So I want to look for the card PK, and maybe it feels weird to sit there and say, well, you're fetching the card PK. Why are you going to the device table first? Well, that's the way in my mind. That's the way I visualize the relationship. Device join card. You can put left out or join on here because that's what we've depicted. But we know that if we're looking for the card name, there's no need for that because we're not going to check against the row where there's no card name where it's null because it was left out. So we can just do the inner join. So we're going to do the join based on the mapping the device's PK against the card's device FK. And then we're going to add the where criteria to plug in our host name and card name. And that's going to flange us down to one unique card in the entire enterprise. And when we did the indexing earlier, if you'll remember, we created an index on the host name, on device host name, okay? And if that index is still here, the optimizer can use it. But we spent all this effort to go write this update so it works correctly, but is it going to work efficient in our distributed environment? When we use the database you just can't kill. What happens when it goes search it, when it applies that where clause for the card name? Well, the optimizer can do multiple things. It's possible for the optimizer to sit there and do everything. The optimizer picks what order it does all this stuff, except it's going to do the update last, but the way it's having to select and find the rows, it's going to pick the most efficient route to do it all. So it can do all the selects and all the joins, and it can apply all the indexes, and it may flange it down to just a handful of rows before it gets to applying the card name where clause. So it may be no big deal. But it's also possible that if I put an index on the card name, if I create index on card name, it can create that. And it's also possible that the nature of the data, it could be that it can flange down faster if it goes to that index first. That would be a case where all the cards are listed, they're ordered, and then you can go back and find a given row in the card table. And if you use card 02 as a host name, it's going to flange it down to all the cards that have card 02. What if there's only one device in the whole enterprise that fits that configuration? In that case, the optimizer can figure out, well, if I go to that first, it narrows it down to a single row of data, and then the rest of the joins are no cost, almost no cost, or millisecond time. And that's where, let me back it up here. Oh, let me do it. Let's do this. Okay. And that's where you can go spend all this effort to write the thing on the left, and you're like, oh, I got the query. Believe me, it's a huge rush to like figure out, hey, I got the query to write. I worked it out. It does the correct thing. I'm going to rush it out to production. And then you get out there, and in your development environment, you've got 1,000, 10,000 rows of data. In production, there's a billion rows of data. And you go run this update, and it chokes the system, especially in a distributed environment. If you suddenly have hit a full table scan that you didn't anticipate, it's rough. And then you're like, what went wrong? The thing is we need to write the query correctly, which is what we focused on doing. We spent a lot of the effort on this live stream working on how do we get the relation? What's the relationship between the tables? What's this one-to-many relationship? Okay, so we can then write the correct update statement. But that's not where it ends. We need to then look at what does it take to optimize the query? What is the thing that the optimizer needs to do its job best? And in this context, it may be an index. And here's the thing, it may not be an index. Like I said, it depends on the nature of the data. And that's why the first couple of episodes on this playlist for the Select Star show is we talked about how to use explain and explain analyze to go figure that out. And that is one of the most valuable things to learn how to do, especially especially in a distributed environment, because it's kind of a cliche to sit there and say full table scans are bad. Okay, full table scans are bad. If you do an update and you're searching on a column and it triggers a full table scan, that's bad. You go to distributed systems and it kills you. Okay. So it's important to understand the tools that are provided so that you can go avoid that. Because the whole thing is, if you're going to have huge data that circles the globe, you've got regional data that is set up. It's good to comprehend that, and you need to be able to apply the right indexes. And so that's the deal, is to build any sort of one-to-many relationship and then to apply the right updates to it. You need to bring all those factors into focus. And that's what we're going to talk about today on doing the one-to-many relationship. I want to let you know, if you want to play with Cockroach DB, you can get a free copy. Well, I mean, let me say this correctly. You can play with it through a free self-paced learning course called Cockroach University. You can scan the QR code if you're looking at this visually. If you're listening to this on the podcast, you can go to university.cockroachlabs.com and then check it out. There's some great courses, Introduction to Distributed SQL. You can play around with that stuff, and actually in your browser, you're playing with a Cockroach DB cluster through your browser. How cool is that? Check it out. And if you're enjoying this kind of content, we'll keep coming back. And the trick is hit the subscribe button and ring the bell, or subscribe to it. You can go search on your favorite podcasting platform and look for Select Star Show, and then you can catch it while you're trekking around town doing all your errands. So how's that for some fun there, Felipe?
Very good. Yeah, we talk about a lot of topics today, and even I, kind of wrote it down. Some kind of I want to do a quick sum up, if you don't mind, for
Go
our
ahead.
audience. Very good. So, guys, we practically talked about cardinality in databases, right? So we start with some kind of a definition, kind of for me, a uniqueness of the data values. Practically, we can have maybe like a very easy features, right, of cardinality. Describe data uniqueness, right, like a high cardinality, many unique values, low cardinality, many repeated values. We talked about indexing, and that's part of the cardinality. It's going to impact indexing and query optimization, right? So high cardinality columns are more selective and often better candidates for indexing, and low cardinality columns may not benefit, obviously, from too much from indexing. Essential in data modeling, right, helps define relationships between tables, right? We talked about relationships one to one to many, and so forth, right? Affects, of course, the storage and performance. Greg did a very good explanation what happened in Cockroach DB, right? Remember, we are doing distributed SQL, right? And of course, it's used in query optimization tools, right? And again, kind of the types of cardinality we have: a column cardinality, high cardinality. For example, most values are unique. The example: social security numbers, email addresses. Low cardinality, few unique values, right? Like a gender, Boolean flags. Medium cardinality, kind of a balanced number of distant values, like country names, department codes. Now we have the relational cardinality, right? The one that Greg explained, like a one-to-one example, like each employee has a unique ID badge, like a one to many, right? Example: one customer can place many orders, like a many to many. Students can enroll in multiple courses. Courses have many students, right? So that's what we talk about cardinality. Then, of course, we start talking about indexing, a kind of the relationship between them. And then we start talking about, Greg asked you a question, right? What happened? What is the drawback if you go for the select star, right? Tell us in the comments, right? If that's about performance issues, maybe there are some changes, unpredictable if you're doing that kind of stuff. Maybe you are not indexing well, and probably that won't benefit a lot. So tell us about that part as well. And we ended doing like a joins, right? Like the inner join, left join, right join. So yeah, we talked about a lot of stuff today, and I like the I like Greg started adding all the drawings. That was very effective, switching between those things. So
Yeah,
so that was
we're at
very
the end
cool.
now, so it's it's like, ouch. Okay. All right, y'all. Hit subscribe. Tune in for the audio show on the again. Go to Spotify, Amazon Music, you name Apple Podcasts, and we will see you next time.
Bye.
This episode is over, but your learning has just begun. Visit cockroachlabs.com to find all kinds of content to expand your knowledge.